Hi everybody, today we're going to continue our discussion on circular motion, but now we're going to look at what happens when you go into what's called a vertical circle, for example, like on a roller coaster where it has a vertical loop, as opposed to what we've been doing up to this point, which has been horizontal circles, kind of just flat circles. One of the major aspects about a horizontal circle, if you think about it, as anything moves around in a horizontal circle, well, gravity's acting on it. Well, of course, gravity acts on everything. But the only direction gravity can act is straight down. So no matter where the object is, its weight, or the effects of gravity, anywhere on the circle, act in the same direction and act in the same way. In other words, gravity really isn't affecting the motion at all. But what happens when things start to go into a vertical circle? Well, as an object moves around in a vertical circle, gravity, of course, still acts on it, and it only acts one way, straight down, okay, no matter where it is in the circle. Now, as we said, whereas this thing in the horizontal circle goes around, the gravity doesn't seem to affect it. But what seems to happen in a vertical circle? Well, if you think about the effects of gravity, as our object is on its way up, gravity, of course, is slowing that upward motion. But as it's on its way down, gravity must be increasing that downward motion. So logically, that means that as the object goes up towards the top of the circle, its velocity must be decreasing. And so the top of the circle must be the location of the lowest velocity you'll probably naturally get in a vertical circle. Whereas on the way down, the velocity is increasing, so the bottom of the circle must be where your maximum velocities are going to occur. Now, keeping in mind, anytime we have circular motion, we have this thing called a centripetal force. And one of the equations we learned for centripetal force is mv squared over r, mass times velocity squared over the radius. Now, if you think about it in a vertical circle, the mass is constant throughout this whole thing, as is the radius. Okay, the radius of the circle is going to be the same everywhere. But if my velocity is the least at the top and the most at the bottom, that must say something about force. And in particular, my forces are going to turn out to be the lowest at the top and the highest at the bottom. Now, there are two reasons it's going to be involved. One is simply the idea of centripetal force. Okay? Maximum velocity should yield maximum force, minimum velocity, minimum force, just in terms of centripetal force. But it turns out that that weight factor also comes into play. So again, gravity is going to affect both velocity and forces in a vertical circle. So your velocity will always be highest at the bottom and lowest at the top. And therefore, net forces are always going to be highest at the bottom and lowest at the top. Now, what do I mean by that idea of net forces? Again, net force is the idea of sort of the sum of all forces acting on an object at any given time or moment. If we consider our mass going around in a vertical circle, I want to consider a couple of points. Here at the top, when it's down here at the bottom, call that bot. Over here, when it is at the side. And we want to look at the sum of the forces at each location. Well, the best way to look at it, free body diagram. Let's start with the top. We consider my mass when it's at the top. Well, there's a string on it that must pull, creating a downward tension. And of course, there is also the weight, which only acts down. Now, if we were to sort of sum our forces here, well, they're both acting in the same direction. Okay? So the sum of the forces would be the tension plus mg, because they're acting together. Now, that should equal ma, right? But notice what direction both of those are pointing if we consider the circle. They're both pointing towards the center, which means if they both act to the center, we consider them both to be a centripetal force. What about at the bottom? Well, at the bottom of the circle, the tension now pulls upward, and of course the weight continues to act down. Now if we sum our forces here, well, tension is up, weight is down. That equals ma, right? But also, those arrows are along the direction of the center of the circle, where the tension is to the center and the weight is away from the center. So again, that relationship, T minus mg, must relate to the idea of a centripetal force. Now, over here at the side, well, weight is down and tension is to the side. Okay? So at the side point, the only thing acting towards the center is the tension at that moment. So the weight doesn't seem to affect it very much in terms of centripetal force there at the moment. Now let's look at these two equations. Tension may not be our force in a vertical circle. For example, a roller coaster going around a vertical loop doesn't have a rope attached to it. So this could be any force, tension, normal, whatever it is. And that's usually the force I'm solving for. So in other words, if I was to solve this for tension from the top, I'd have T equals Fc minus mg. If I were solving it at the bottom, I'd have T is Fc plus mg. Okay? Now, that kind of explains why forces are minimum at the top and maximum at the bottom. See, whatever force I have at the top of the circle consists of centripetal force with a low velocity, but then I have to subtract out the weight because the weight is kind of helping me stay in that circle. I'm not really acting against it. However, at the bottom of the circle, I have a maximum centripetal force because my velocity is maximum, plus I have to support that additional weight pulling down. So that's why my forces are always greatest at the bottom. And now that gives me two relationships for a vertical circle. Any force in a vertical circle at the top is found by the centripetal minus the weight. Any force in a vertical circle found at the bottom is the centripetal force plus the weight. Let's look at an example. Here's an example of a roller coaster going through a vertical loop. Most roller coasters aren't perfect circles. They're actually teardrop shaped. That gives actually a better ride and a better loop through it, but we'll pretend it's a perfect circle here. So our roller coaster car that has a mass of 500 kilograms is going around this vertical circle. And we're given the fact that it has a velocity of 20 meters per second as it comes right through the top. And the radius of the circle is 20 meters. First question, finding the force that the track exerts on the car at the top of the circle, okay, which actually would be a kind of normal force here. Well, that first part is not too difficult because we know the force at the top is the centripetal minus mg. Now all we've got to do is do a little substituting. Centripetal force is that equation, mv squared over r. And then this is kind of nice and easy because we know all the numbers. All we got to do is plug it in. Mass is 500, velocity is 20 squared, radius is 20, minus 500 times gravity is 10. And we get a force of 5,000 newtons acting on the car at the top of the circle. Okay, pretty easy to start, right? My second question, though, says determine the velocity of the car right as it comes through the bottom of the loop. Now, this is the most common mistake that is often made. Some people will try to use that force at the bottom equation to find the velocity, and they'll put 5,000 newtons as the force. But we already know that the force has to increase as we go to the bottom of the circle, because it's going to be greater than the top. So how do we get that velocity at the bottom? Well, easiest way is always to go back to our old friend energy. Now be careful here because at the top of the circle, do we have height? Yes, definitely. Do we have motion? Yes, we better have motion because if that car stopped there at the top, the next place it would go is straight down. Not very good for our roller coaster riders. So since we said yes to both, we have gravitational potential energy and kinetic energy at the top of the circle. Now as it comes to the bottom of the circle, do we have height? No, we're at ground level. Do we have velocity? Definitely. So we only have kinetic energy at the bottom. Now, assuming no friction, we can say that the total energy at the top is the total energy at the bottom. We have gravitational potential energy and kinetic energy at the top, and just kinetic energy at the bottom. Potential energy, mgh, kinetic, 1/2 mv squared at the top, kinetic 1/2 mv squared at the bottom. Now it's the same roller coaster all the way through, so if we want, it's always nice to be able to cancel out the mass here. We do a neat little thing. Let me multiply through by 2. That gives me 2gh, gets rid of the 1/2 on that side, and gets rid of the 1/2 on the other side. Looks a little bit like the time unknown equation, doesn't it? So, gravity is 10. Oh, the height. What's the height? Well, the height is the same thing as the diameter of the circle. So we just have to double the radius. Don't forget to double the radius there. Velocity at the top was 20. This is 800. That's 400. So the velocity at the bottom squared is 1200. And then if you take the square root of 1200, you get about 34.6 meters per second. Now, that bottom velocity is very important in order to solve this last question: how much force does the car experience at the bottom? Well, vertical circle, force at the bottom is centripetal force plus mg. Again, mv squared over r for our centripetal force. Mass is 500. Oh, you know what? We could put in 1200 for v squared. We already knew that. Radius is 20. Mass is 500. Gravity is 10. And that gives me 35,000 newtons. Okay, 7 times more force at the bottom of the circle than at the top, which is why you feel a lot heavier as you come through the bottom of a loop, because you're experiencing a greater force. And that's basically how that's done. There's one other thing that occurs within a vertical circle that doesn't occur in a horizontal circle. I want to look at a little simulation to show you what I'm talking about. Here I've got a skateboarder and a vertical loop that's set up. Now, if I was to start my skateboarder on a ramp here into the loop that was equivalent to this point right here, okay, at about 7 meters, which is the top of the loop. If we let him go, he goes down into the loop, and whoops, didn't make it all the way through, did he? Okay, he didn't have enough velocity at the top of the circle in order to get through. And that should make sense, because if he had a velocity of 0 here at 7 meters, well, that means he would have a velocity of about 0 here at the top of the loop, and that means he's not going to be able to make it through. So it turns out he needs a lot more speed. Okay, let's drop him from up here. Now you notice he's slowing down, but oh, had just enough speed to get through that loop. So it turns out you need a very, very specific amount of velocity in order to get through a vertical loop. That particular velocity is something called a critical speed. And it's basically a speed that is required to maintain a vertical circle. And there's a specific equation that goes with it. The critical speed of a vertical loop is the square root of its radius times gravity. Notice the mass of the object doesn't really matter, so it's true for any object in a vertical circle. Now, the interesting thing is it can be a minimum speed or a maximum speed. In other words, if I have a loop like the roller coaster loop with a certain radius, well, remember, I'm going to have a low speed here at the top. So my critical speed when I'm inside the loop is also the lowest possible speed I need. Okay, so that critical speed, square root of Rg, I need to maintain that speed as a minimum. Okay, any slower, I'm going to fall out of that loop. But it turns out a hill also has a critical speed going over the top. But now here the critical speed is a maximum you can attain. Because if you go faster than that critical speed, you'll leave the top of the circle. And again, sometimes they do this with roller coasters where you're going over a hill. They actually make the car exceed the critical speed. And that's why you seem to come out of your seat, because you're going too fast to go over that hill. Luckily, the roller coasters have under-track wheels. Okay, so for example, in that previous example of the roller coaster loop, where here we had a roller coaster loop with a radius of 20 meters, the critical speed of this loop would be the square root of RG, or the square root of 20 times 10. In other words, that roller coaster car has to maintain a speed of at least 14.14 meters per second coming through the top, otherwise it would fall out of that loop, especially if it didn't have under-track wheels. Okay, so that's basically the idea of vertical circular motion. Keep in mind, in vertical circles, unlike horizontal circles, your velocity can change. Your velocities are going to be lowest at the top and highest at the bottom due to the effects of gravity. Your net forces will also be lowest at the top and highest at the bottom. And again, this is because of both centripetal force and the idea of how gravity affects it. And finally, that idea of critical speed, the speed you need in order to actually make it completely through safely in a vertical circle. All right, we'll see you next time.